Welcome back. If you've been watching the videos and keeping up to this point, we've mastered linear regression and classification. But here's the hard truth. The real world isn't a straight line, and simple models can only take us so far. So today, we are crossing the threshold into true deep learning. We are taking our basic mathematical tools and wiring them together to build our first actual neural network, the Multilayer Perceptron, or MLP. So the MLP solution handling nonlinear data. So why can't we just keep using our simple models from the last few videos? Because they are fundamentally linear. Imagine trying to predict a coffee's overall quality rating based on a bean evaluation and roast time. A simple straight line can't capture the complex, sweet spots where all those variables interact. To solve nonlinear problems, we have to add what we call hidden layers between our inputs and our final outputs. And these hidden layers allow the network to build hierarchical features instead of just looking at raw numbers. The first hidden layer might combine simple stats, the next layer identifies broader flavor profiles, and the final layer uses those concepts to make an accurate prediction. Activation functions finding the right signal. Here's the catch. If you just stack a bunch of linear layers together, the math dictates that they collapse into one giant boring linear equation. To actually bend our decision lines, we have to inject non-linearity at every neuron using activation function. We used Sigmoid earlier, actually last video, and there's another popular one called Tanh. But in deep networks, both of these suffer from a fatal flaw called vanishing gradient problem. When numbers get really big or really small, the curves flatten out at the top and bottom. When the curve is flat, its slope, its gradient drops to zero. The network stops learning completely. Enter ReLU, or as you can see, ReLU, rectified linear unit. So the math is really simple in rectified linear unit, ReLU. If the input is negative, make it zero. If it's positive, leave it alone. Because it never flattens out on the positive side, gradient stays strong. Computation is lightning fast, and it has become the absolute industry standard. Data flow and loss. Now let's look at how this machine actually runs. It happens in a two-step cycle. Step one is the forward pass. This is where the model makes a guess. We take our data and feed it into the input layer. The numbers flow forward, getting multiplied by weights and added to biases and transformed by our ReLU activation functions, layer by layer, until a prediction pops out at the very end. We then check that prediction against our loss function to see how badly we missed the mark. Backpropagation and parameter update. Step 2 is the backward pass, better known as backpropagation. This is the holy grail of deep learning. So if you remember from video 1, the chain rule, this is where it shines. Starting from our final error score, we work backwards through the network layer, layer by layer. The chain rule lets us calculate exactly how much each individual weight and bias inside that massive web contributed to our mistake. Once we know who to blame, we use gradient descent to nudge those numbers in the right direction. And you repeat this forward and backward dance thousands of times, and that random grid of numbers gradually transforms to a powerful, intelligent model. So backpropagation, I did make a previous video about this, kind of like working backwards. So we officially have a working deep neural network. But when you build models with this much capacity, a whole new set of practical disasters awaits you. In the next video, we're looking at why deep learning models fail in the real world, tackling overfitting, regularization, and the optimization tricks that keep our networks in line.